to introduce Helmut Bölcskei from ETH in Zürich to give today's seminar talk. And just as a reminder, actually Helmut has two appearances today, one in the seminar this morning, and then one for the Distinguished Rothschild lecture this afternoon at 4 p.m. UK time, where he will give a more general audience presentation about the mathematical mysteries of deep neural networks. So let me say a few words about Helmut before I hand over the word to him. Helmut is a professor in electrical engineering and mathematics at ETH in Zürich. In his research, he made fundamental contributions within the areas of information theory, mathematical signal processing, machine learning, and statistics. For his contributions, he was awarded several prizes and honors, and there are too many to name them all, but let me point out a few. He was a recipient of the 2001 IEEE Signal Processing Society Young Author Best Paper Award, the 2006 IEEE Communication Society Leonard G. Abraham Best Paper Award, the 2010 Vodafone Innovations Award, and the ETH Golden Owl Teaching Award. He is also a 2011 EuroSIP Fellow, and he was a distinguished lecturer of the IEEE Information Theory Society, an Erwin Schrödinger Fellow of the Austrian National Science Foundation, and he was included in the 2014 Thomas Reuters list of highly cited researchers in computer science. He was an editor-in-chief for the IEEE Transactions on Information Theory. He was the TPC co-chair of the 2008 IEEE International Symposium on Information Theory and the 2016 IEEE Information Theory Workshop. And he served on the board of governors of the IEEE Information Theory Society. It's really a big honor that Helmut agreed to speak twice today, and starting with his talk this morning on fundamental limits of deep generative neural networks. Helmut, the stage is yours.
Thank you very much, Carola, for the very generous and exhaustive introduction. I appreciate it. Welcome, everyone. Good morning. It's a pleasure to be here. I would, of course, have preferred to come physically, but I guess you all know why it didn't work out. So I would like to talk a little bit about the recent work we did on deep generative neural networks. And this is joint work with my former PhD student, Dmytro Perekristenko, who just graduated in June, and a former master's student from the math department, Leandre Eberhard. The successes of generative networks are too many to list exhaustively, but just to give you a few examples. So generation of photographs of human faces. So these are actually human faces that, I mean, these human beings don't really exist. They were generated by neural networks. These networks were trained on the faces of celebrities. So you will probably recognize some features of celebrities in this image. This was Carlos in 2018. Or text-to-image translation. So you give a text to the neural network, like the small bird has a red head with feathers that fade from red to gray, from head to tail, and out comes an image of such a bird. Or this bird is black with green and has a very short beak, and you get those wonderful images. Photo in painting. So you have incomplete pictures. Let's say you have a fresco and you have parts missing. So there's what is called GAN context encoders. They can, based on the context, fill in those images, a classical task in mathematical signal processing. And there's many, many more. I don't want to go into this. You may know this photos to emojis. This is something my son likes to use on his smartphone. So let me just stop here. And there's a web page. You can see all these wonderful applications of GANs. And go into the mathematics that we want to do today to try to understand a little bit why all these things are possible. So what we want to do is we want to study what is fundamentally possible with a deep generative neural network. We are going to ignore the aspect of training. So there's going to be no talk about training here. We are going to assume that we have access to infinite amounts of training data. and we have the optimal training algorithm. Usually there is a generator discriminator training algorithm in GANs. So you have a network that generates, let's say, target images, and those are fed to a discriminator network. And that discriminator network is to decide whether this was actually generated or a true image. And then the two networks duel. So this is a game theoretic contest, and then the idea is that once you're done with training, that the GAN would be so good that it can fool the discriminator network with very high probability. In particular, if you want in more mathematical terms, we are going to be interested in generating probability distributions. And not only that, but we will be interested in generating probability distributions that are high dimensional from low dimensional inputs, in particular from a one-dimensional input, a uniformly distributed random variable on the interval 0, 1. And why low to high dimensional? I will try to explain. First of all, it appears in practice, this problem of generating high dimensional outputs from low dimensional inputs, for example, in natural language processing, where you want to predict the next word in a text sentence, in text sequence, sorry. So the input layer would be determined by the dimension of the word embedding. So this is a way of mapping words into a Euclidean space, with the idea being that words that are somehow contextually close by would also have a small Euclidean distance in the embedding space. So that dimension is typically around 100. And the output layer of the network that generates this text would be a vector of probabilities for each of the words in the vocabulary, typically about 100,000. So you see here we go from low to high dimensional. Now, why else would we want to go from low to high dimensional? Well, first of all, we want to understand fundamentally what is possible. Secondly, these results in very parsimonious networks. If input dimensions are low, then altogether, these networks will be smaller, and it requires less training data because the network is less complex. So here is a definition of a neural network. You have certain input nodes, then you have so-called hidden layers in blue, you have output nodes or an output layer, and the image indicates that you go from low to high dimensions. And you compose affine mappings with no linearities. So the transition from layer to layer entails an affine transformation AX plus B, followed by an element-wise application of a nonlinearity. So more formally, you can see this here. A neural network is a map phi that takes the input, applies W1 and affine transformation to the input, applies the nonlinearity rho element-wise, and then applies the affine transformation W2, and so on and so forth. Typically, or in this talk, we are going to use the ReLU activation function, max of 0 and x. The notation that would be good if you could, take and keep it in mind as we go through the talk is M. M is the total number of non-zero parameters across all the affine transformations. So if you like, it's the connectivity of the neural network. L is the depth, the number of layers, and W is the width of the network. So if you remember from the previous slide, this is just the maximum of the number of nodes across all layers. And the notation we're going to use is calligraphic N for a neural network, subscripted with the number of inputs, D, and the number of outputs, D prime. So M, connectivity, L, depth, and W, the width of the network. So these are quantities that in a sense measure complexity of the network, but eventually we'll end up measuring complexity of the network in terms of the number of bits needed to encode the topology and the quantized weights of the network. This will be something that I would like to briefly discuss at the end. Okay, so summarizing, what is our goal? We have a uniformly distributed random variable on the interval 0, 1. We pass it through a neural network with one input and D outputs, in this case here in this image, 2 outputs, and we have a target distribution Pxy, and we want to generate or approximate this target distribution. The question is this possible at all, and to what extent is it possible? And can we quantify the approximation error? And the main result of the talk will be that you can generate any target distribution out of this U01 random variable, and you can make the error in the approximation of your target distribution as small as you wish by choosing the network properly. So in other words, a good training algorithm, and if you have sufficient data, is going to find an arbitrarily good approximation to any target distribution that you can think of. So that's something like a universal approximation theorem for generative neural networks. Okay, now the mathematics behind this is really based on an ingenious idea by Dmitry Yarotsky back in 2017, who observed the following. So he said, well, if you have a ReLU network, you generate piecewise linear functions because the ReLU function is 0 for negative x and identity for positive x. And if you have linear combination of shifted and scaled ReLU functions, you get a piecewise linear function. There is one particular piecewise linear function that he looked at and recognized something. This is the self-composition property that I want to identify here. So let's suppose you start with the function g1 of x. So you have this, what we call the head function. Now this head function can be realized through a neural network by taking 2 times rho of x minus 4 rho of x minus 1/2 plus 2 rho of x minus 1. So rho is the ReLU function. And then you can easily verify that if you have this linear combination of these shifted inputs and apply the rho functions, that you get this head function. And the key insight that Yarotsky had was the following. What happens if you compose G with itself? Now, if you compose G with itself, then you see, looking now at the second picture, G2 of x, as you traverse from 0 to 1/2, on the left-hand side, you traverse from 0 to 1. So as you traverse from 0 to 1/2, you have essentially traversed your head function once. And then if you are at 1/2, then you would be here. And you go and continue to 1, then you go back from 1 to 0. Since the head function is symmetric, you produce another head. So that gives you a double head. Now, what happens if you continue and you compute G, composed with G, composed with G, then you get a quadruple head function, and so on and so forth. And usually in approximation theory, this property is then used to realize that you can generate oscillating functions, and you can generate Fourier series. And once you can generate Fourier series, you can generate continuous functions, and so on and so forth. Here we are taking a different route in GAN theory. What we are going to use here is the so-called space-filling property of this construction. You can already guess that if you continue this composition ad infinitum, you're going to get something that will fill out your graph here, and I will show you a picture later on. But before we talk about the space-filling property, what can we expect from ReLU networks in terms of the output distributions that they can generate? Well, in very simple mathematical terms, since a ReLU network generates a piecewise linear function, if you apply a piecewise linear function to a uniform random variable on the interval 0, 1, so you push forward your input variables through a piecewise linear function, what you're going to get is, as depicted here on the right, a so-called histogram distribution. And the way you can think about the picture on the right is as follows. If you start here on the left and you look at the interval 0 to 1/4, then you see that the slope here is 2. And then a simple calculation shows you that the histogram bin will have 1/2 in terms of height. Now you continue, you have a slope of 1. So the histogram, the bin is going to have height 1. And here you have a slope of 1/2. So you're going to have a bin height of 2, and so on and so forth. All right, so we know now that ReLU networks can generate histogram distributions. And I'm sure you already see where we are heading. So this would be a 2D histogram distribution, and of course you can do this in any dimension. If you summarize what we want to do is we have a target distribution, and we are going to stick to 2D simply because all the main ideas can be conveyed in 2D, and the general high-dimensional case is really messy in terms of notation, and I don't think it's eminently teachable. So you have U01 random variable, you pass it through a neural network with one input, two outputs, and we just found that this generates a histogram distribution 2D. And then you can control the error, the approximation error, by making the histogram bin size sufficiently small, and that gives you your target distribution. What is interesting here is actually that we want to go from 1 dimension to 2 dimensions. So the question is now, do we have enough randomness in this input random variable to generate any given target distribution in 2D? So we have to go from 1 dimension to 2 dimensions. And here is where Jarodsky's idea comes into play. We're going to do this through what we call the space filling property of sawtooth functions. So if you look at the picture in the center, then this is the composition of the G function with itself a certain number of times. And then you see if you push forward your uniformly distributed input random variables through this sawtooth function, what you get is that the slope here is always the same, either positive or negative, but the same magnitude. So you are painting essentially your 2D, your square with probability mass. And as you let S, the number of compositions, go to infinity, those T's will become tighter and tighter, and you're going to fill out the entire space. And here's the mapping M going from 1 dimension to 2 dimensions. So now the question is, where do we get the randomness from that we need out of this uniformly distributed 1-dimensional random variable to generate a 2-dimensional distribution? And if you like, you can think about it in terms of the binary representation of the input variable. Since it's uniformly distributed, the bits in its binary representation are going to be independent. And what you see is that the G function, not GS, the G function generates either X or 1 minus X, depending on whether you're in the interval 0, 1/2 or 1/2, 1. So what happens when you generate 1 minus X? You perform bit flips. And then you can sit down, you can very easily work this out. And it's actually these bit flips that give you this randomness because the individual bits are independent. So you're picking out individual bits, and you know, you take the U01 random variable, you take every even indexed bit and every odd indexed bit, and you have 2 independent random variables, again, uniformly distributed. So that, if you like, is the mathematical key idea of this talk. There's not going to be all too much more in terms of mathematics after this. Now we just want to put it together. And what I mean by put it together is, how do we realize general 2D histogram distributions? Now, to see this, you write a general 2D histogram distribution in this form, sum over K1, K2, you have the weights, WK1, K2, and you have the indicator functions on those boxes. And the boxes have area 1 over n squared, so you have n boxes in each direction. Then you write WK1, K2 in this form here. So you see that there are probabilities involved, and we're writing P of X1, X2 as P of X1 times P of X2 conditional on X1. So that's what's happening here. That takes you to the third line. And you see here we have a histogram distribution and another histogram distribution, but conditioned on K1. So for each different value of K1, we need different histogram distributions. And in particular, on the previous slide, I showed you only how to generate uniform distributions. But now we need general histogram distributions with general weights. And the question is, how do we get that? And this is essentially the last idea that I wanted to convey, namely, we adjust the paint plan. So if you like, that's the main insight here in making things work. Namely, if you have your function f, it's the output of a ReLU network, piecewise linear, then what I mean by adjusting the paint plan is that you decide, let's say in the interval 0 to 1/4, to spend a little less time, in the interval 1/4 to 1/2 to spend a little more time. And if the paintbrush moves at the same speed, you're going to leave behind or deposit less and a bit more and even more probability mass. So the longer you travel through this interval, the more probability mass you're going to leave behind. And you see this on the right. So we have here 1/2, 1, 2, and 1/2. So that gives us a distribution that actually is general in the X2 direction, but still constant in the x1 direction. And the last idea, before I explain that, I want to mention that what is important here is that f is piecewise linear, so it can be generated by a ReLU network. GS of x can be generated by a ReLU network simply because G can be generated by a ReLU network, and the composition of G with itself is again a ReLU network, and the composition of the result thereof with f is again a ReLU network. So the operations we are allowed to perform here, they should be realizable through ReLU networks. So this is the case here. So the last thing that remains is that we should actually be able to get different conditional distributions as we go here along the x1 axis. And this we do by squeezing and summing up. So what I mean by squeezing is we perform this affine transformation. GS of n, fx1 of x is actually the random variable in the first coordinate minus I. So if you try to find out where this is, this random variable here is going to be located, you simply set n f of x minus I equal to 0 and equal to 1. And you see that if n is equal to 4, you're going to compress into the interval 0, 1, 4. 1/4, sorry, and then as you traverse through all possible i's, you get those different blue, orange, green, and red, those different distributions. And fi is actually your piecewise linear function. It may be different for different i's, so you can have different paint plans across those 4 different boxes, and that gives you a general 2D histogram distribution on the right here. What is important here is that as opposed to the idea as we had seen it before, where we have x, f of g, s of x. I mean, it's essentially present here that in the second component or coordinate, we actually have the first component here as an argument. And likewise, you do the same thing here. We need to paint with a general paint plan already the first component, and then we take this first component and we stick it in here, we squeeze and we sum up. And last comment about this construction, f of x is actually piecewise linear, can be implemented with a ReLU network. N times f minus I is an affine transformation. Affine transformations are realizable through ReLU networks. GS can be realized through a ReLU network. The composition of ReLU networks is again a ReLU network. So the composition of GS with NF minus I is again a ReLU network. You compose the result thereof is Fi. Fi is piecewise linear. It's again a ReLU network. You sum up, sums can be computed with ReLU networks. So everything we do here can be realized through a ReLU network. So that's essentially the rules of the game are such that you can do whatever you like. You're gonna get things to work out as long as you have only operations that can be realized through ReLU networks. Okay, good. So now comes the part where we want to understand how good these approximations are and how good we will measure in terms of Wasserstein distance. Remember, if you have 2 distributions, mu and nu, then you look at the set of all couplings between mu and nu, and a coupling is actually a joint distribution that preserves the marginals as mu and nu in this case. And then you're looking at the inf of the expectation of your distance here, Euclidean distance, with respect to those couplings. So you're measuring, as you know from optimal transport theory, what it costs to transport mu into nu, and the cost here is measured in terms of Euclidean distance. So that's going to be our measure, not only because, well, you can easily quantify things in that measure, but also because it's a measure of choice in GAN's theory. Wasserstein distance is one of the distance measures that is being used. Okay, the first result is the following. If you want to generate a histogram distribution, so px in epsilon 0, 1, and d means px is a histogram distribution with n bins. The target space is d-dimensional. There exists a ReLU network that generates this histogram distribution. The network connectivity is of order n to the d. N is the number of bins. D is the output dimension. S is essentially the number of compositions, or essentially the depth of the network. L is proportional to S times n to the d minus 1 here in M. And the network is such that the Wasserstein distance between your target histogram distribution and the distribution that you get by pushing your U01 random variable through your neural network is upper bounded by this quantity on the right-hand side. And there are two insights here. One is you see that if you take S to infinity, meaning the number of compositions of the head function with itself, meaning that the depth of the network goes to infinity, so you get to be arbitrarily deep, you can make this error as small as you wish. And the second is that if you want to measure complexity in terms of the connectivity of the network, you see that if you take, for simplicity, S to be proportional to N, that the connectivity is proportional to N to the D. N is the number of bins, D is the output dimension. So that's really the number of free parameters you have in your D-dimensional histogram distribution. You have simply N to the D bins, and each bin has a weight associated with it. So in that sense, there's a certain minimality property here, but we're going to be a bit more rigorous about this minimality property later in the talk. So that's for histogram distributions. The question is, what can we do for general distributions? And we will answer that question. But before we do that, what I would like to tell you is that in GAN theory and general neural network theory, usually you work with real valued weights. So the question is now, well, in real valued numbers, I mean, you can stick in every real valued number infinitely many bits. So the question is the construction that we have here, the space filling property, is it very brittle? Does it depend on the ability to have real valued weights? Are we hiding something in those infinitely many bits that we can stick into each real valued weight? And the answer is we'll find no. And we're going to look at GANs with quantized weights. So the values the weights can take are from a finite set, and the set size can grow with the approximation error, but we discretize. And finally, we do that also because it will allow us in the end to understand how the complexity of generating networks that generate a target distribution to within a certain error epsilon, in how the complexity in terms of the number of bits needed to represent a network compares to the complexity of the class of target distributions it tries to realize. Okay, so it answers the brittleness question. It should convince you that we're not hiding things in the weights being real valued, and it allows us to do some quantization theory at the end of the talk and measuring the complexity of those generating networks. Okay, so here is what we call the universal distribution approximation theorem or realization theorem. For every distribution nu, so not necessarily a histogram distribution, on the interval 0, 1 to the D, there exists a quantized ReLU net. Never mind the details about this delta divided by n quantized. This is not really relevant here. With connectivity as before and depth as before, such that the Wasserstein distance between the target distribution nu and what we generate through our neural network is upper bounded by a sum of three terms. The first one you have already seen, square root of d divided by n times 2 to the s. So that is the penalty that you get from increasing your dimensionality. The dimensionality increase you can get by taking the network to be deep, meaning that S, which is proportional to the depth of the network, has to go to infinity. The second error results from the histogram distribution. Remember, ReLU networks generate histogram distributions. From the histogram distribution, trying or approximating your target distribution. And the third error is induced as we quantize our neural network. So that's what we call the quantization error. So in summary, you can get your dimensionality increase penalty to go to 0 if you take the network depths to infinity. You can get the histogram approximation error to 0 as you increase the number of bins or you reduce the bin size. I mean, this is something we would expect. And the quantization error you can drive to 0 if you pick the quantization interval delta. So essentially what this delta divided by n quantized means is that the weights are integer multiples of delta divided by n. if you pick delta proportional to 1 over n squared, then here your delta is 1 over n squared. So you get overall 1 over n. And as you take n to infinity, the quantization error goes to 0 as well. So that's the, there are the three issues: dimensionality increase, histogram approximation error, and quantization of weights. And for example, if you have a histogram target distribution, then the second component would not be present. If you work with real valued, i.e. unquantized weights, the third component would not be present, and you would be back to the result that you have seen before, namely this result here. Okay, good. So what is the main conceptual insight? Before I state this, I did not mention how you could generate a target distribution of d-dimensions very easily. I mean, you could just have a push forward through, I mean, you start with a d-dimensional random vector, and you generate your target distribution by pushing forward through the appropriate function. And you just have to characterize the push forward measure, and you are done. However, you would be going from D, let's say, independent random variables to D independent random variables. And there are methods of doing that, and there's Box-Muller method and so on. The question here was in this talk, can we extract from a single random variable enough randomness to get any d-dimensional target distribution? The answer is yes. And in particular, if we take our generating network to be deep enough, the histogram size to be, or the number of bins to be high enough, and the quantization to be fine enough, then we are not going to pay a penalty in terms of Wasserstein distance as compared to the case where indeed we generate the target distribution from D independent random variables. And as I said before, the way you can think about it is in terms of the binary representation of the input random variable, where the individual bits are independent. So you can just take the polyphases. So the zeros, the m's, the two m's, the first, the m plus first, and so on. And so if your D is finite, you can generate enough randomness. So that's, and indeed, it turns out that if you look carefully at these networks that we construct, they actually do have this bit allocation property, bit flipping properties, and so on. But I don't want to spend more time on this. So that's, in a nutshell, the main conceptual insight. Now, before concluding, I would like to close the circle and come back to this issue of complexity that I mentioned before. In particular, so what we have is, if you have a uniform 0-1 random variable, and we have a d-dimensional target distribution, and we have a quantized network, our network encodes the target distribution. So the inputs are always U0-1, and different networks generate different target distributions. That means that you can view the network as a way of representing a target distribution. The question is, how complex is this representation? And since we work with quantized networks, we can describe our networks as bit strings. In particular, what are the two components that we have to encode? One is the topology of the network. What I mean by topology is the locations of the non-zero weights. So which nodes across layers are connected and which are not. I mean, layers are only connected, only adjacent layers are connected. So you record carefully as you go from one layer to the next, where you have connections and where you don't. This is what we refer to as the topology of the network. And that's one part. And the second part is, since you have quantized weights, you can represent them with finitely many bits. And that's the second component that you have to encode. So now, question, how many bits do you need to encode a network of connectivity M? Now, if you have a network of connectivity M, then the depth of the network can be no more than M. The width can be no more than M. And then you count the total number of weights that you can have in the network. And in each layer, you can have no more than M squared weights for the affine transformation, plus M weights for the bias vector. Remember, the affine transformation is AX plus B. So the matrix A is M by M, the vector B is M dimensional. So that gives you M squared plus M. Either you are wide, then you have and if you're deep, if a network is ideally deep, then you have L proportional to M. So you multiply M squared plus M by M, and you get an M cubed type behavior. Now, if M cubed is what you get, then how many possibilities do you have to allocate M non-zero weights among those M cubed possibilities? It's M cubed, choose M. And then you have a lower and an upper bound for the binomial coefficient, which is proportional to M squared raised to the power of M. So it's M to the 2M, you take the log. So you have M log M bits that you need to encode the topology. If you have M log M bits that you need to encode the topology, you see here actually that M is proportional to N to the D. Now, if you set your approximation error, forget about terms 2 and 3 here, to be proportional to this here, then I'm not going to go any further because I think it's already, I mean, I'm really missing the blackboard. I'm sorry about this. But if you set epsilon equal to this error here, and you work with M log M, which we just found, and you replace M by N to the D, then you actually see that you will get a rate distortion optimal result. That's in a nutshell what's going on this slide and on the next slide. However, what we want to do is we want to compare to the fundamental limit, and the fundamental limit in terms of distribution representation is something that comes out of quantization theory. So in case you don't know this book by Graf and Bölcskei in 2000, it's a wonderful book on quantization theory that I highly recommend. And they have studied this question. What they have studied is the minimal n-term quantization error of a general non-singular distribution nu supported on 0, 1D. In terms of Wasserstein distance, so you have a measure, discrete, you have no more than n points, and V subscript n of nu is the smallest approximation error you can get to your distribution nu with an endpoint probability distribution. And what they found is under very mild moment conditions, this is the theorem 6.2, this is the condition, the moment condition here. Do you get the asymptotics of this error, Vn of nu, to behave exactly the same for all these distributions? Namely, if you have n times 1 over d times epsilon is equal to c, then you see that epsilon is proportional to n to the minus 1 over d. So the number of points that you need in order to get your error to be less than epsilon is proportional to epsilon to the minus d. So those of you who work with metric entropy will already have seen that we have a covering argument. We are covering the space of probability distributions with epsilon balls. So V is less or equal than epsilon. How many balls do we need? We need order epsilon to the minus d. What's the metric entropy that we need at least? It's lower bounded by d times log 1 over epsilon. So this is a covering argument. And the question is now, how does the generative network that we have constructed fare relative to this fundamental limit? And the answer is, indeed, if the target distribution is a quantized histogram distribution, your neural network achieves this covering limit. Namely, the statement is the following. Consider the class of quantized histogram distributions. Then there exists a set of quantized ReLU networks, phi, depending on epsilon, the approximation error, of cardinality 2 to the L of epsilon. So L of epsilon is essentially the metric corresponds to the metric entropy, where L of epsilon behaves like the fundamental limit. And then, of course, there's dependence of the constant on the ambient quantities, such that the Wasserstein distance error, the worst case error across all distributions that are quantized histogram distributions of a given bin width and given output dimension is less or equal than epsilon. So a classical covering argument just in the space of probability distributions. So in the case of quantized histogram distributions, neural networks are indeed optimal in the sense of the description complexity. Now I want to point out that this lower bound here we get in metric entropy is very rough, d times log 1 over epsilon. why is this lower bound not all too surprising for quantized, for quantized histogram distributions? Well, if you have n bins, you have n real numbers that you want to represent. What's the metric entropy of a real number on the interval 0, 1? It behaves like log 1 over epsilon. Just quantize uniformly, and that's what gives you a log 1 over epsilon behavior. And if you have more parameters, I mean, this is just the number of parameters times log 1 over epsilon. So the scaling behavior remains the same. But as you know from metric entropy theory, if you have more general functions, for example, if you have the set of Lipschitz functions, then the metric entropy scales exponentially in epsilon to the minus d, if d is the ambient dimension. So it's actually epsilon to the minus d bits. So the log scales like epsilon to the minus d. So it's to be expected that if the distribution becomes more general, that this simplistic lower bound, of course, is not going to be achievable. Nevertheless, what we can find is the following. If you have the class of general distribution supported on 0, 1D, and we denote this class by calligraphic F, then with quantized ReLU networks, you can actually approximate to within an error of epsilon with metric entropy like quantity, or with a number of bits that behaves like epsilon to the minus d times log squared of 1 over epsilon. And we don't know in that case if we can achieve optimality or not, but I suspect if you work it out for certain classes of distributions, I mean, there you have to go and be a bit more specific that in terms of the scaling optimality will be retained, but it's something we cannot prove at this point. All right, that brings me to the end. So thank you so much for listening, and I'll be delighted to take any questions you may have.
Thank you so much, Helmut. Thank you so much for a really great presentation. Lots of clapping from the audience, as you can see. Do we have any questions? So I suggest you can either unmute yourself, or maybe follow Yuri's example. He's raising his hand and I'll allow him to speak in a moment. Or you can also type your question into the chat if you feel more comfortable with this. So Yuri, I'll hand over to you.
Thank you very much for the very interesting talk. I had to raise my hand on Zoom because there's no one to chair me in this room. So I have to pretend I'm online. So my question is about the space filling idea. I think it's a very elegant idea. But on the other hand, space filling curves are by definition unstable, sort of discontinuous, if you like. So I suppose you would not be able with this method to control where you sample. So if your sample on 0, 1 is, say, 0.5, you would end up in 1 bit of your high dimensional distribution. If it's anywhere near, if it's very close to 0.5 but not exactly 0.5, you would end up somewhere completely different on your distribution. Is that true, or did I misunderstand something?
No, that's true. And so thank you very much for the excellent question. I fully agree with what you say, and I can make it even worse. Unfortunately, this so as ingenious as Jarodzky's construction is, and I think this is probably one of the elephant in the room of representation theory, and what I presented here is the following, that this idea that as you self-compose G, that you get the number of linear regions to scale exponentially in the depths. So each composition adds 1 layer to the network. So I showed this picture. We started with the head function, then double head, quadruple head, and so on. So the number of linear pieces is 2 to the depths of the network. You are not going to get this with trained networks. What I mean by trained networks is, I mean, the network that you get if you compose G with itself, it's highly stylized. I mean, the weights, I showed this construction. So the head function is 2 times rho of x minus 4 times rho of x minus 1/2 plus 2 times rho of x minus 1. So you have the weights 2 minus 4, 2, 0, minus 1/2, minus 1. And as you compose G with itself, I mean, you have very specific weights that you get. And then you can ask yourself, well, what if I perturb those weights? And then the number of linear regions, the scaling, actually breaks down, at least numerically, this is what we see, from exponential to something polynomial. Mm-hmm. And then that's really bad, because then also in approximation representation theory, you can't get all these beautiful results in practice, and likewise actually in what I presented. So I think that's the Achilles heel of all this, and thank you very much for pointing it out. I had planned to mention it, but I totally forgot.
Yeah, well, thank you. And is this actually, can you actually see this effect just because you cannot represent these twos and fours and whatever exactly on computers? Is that already bad enough, or?
Yeah, no, you're not. Your training algorithms are not going to find the 2 exactly and the -4 and the -1/2 and so on, right? Yeah, I mean, you're going to find real numbers, and I mean, what's the probability of the training algorithm giving you, you know, all the weights from a small a set of small size?
But can you force these weights to be 2s and 4s and only train the rest?
Yes, well, there is a wonderful paper by, I think the name of the person is Ivan Odelets. He's at the Skolkovo Institute of Technology. The paper is called Growing Axons, and that's precisely the idea that you build a network with all those 2s, -4s, and so on, and you train only the last layer. But then there's other issues that come up. I mean, I don't want to, so I encourage you to look at that paper, but the paper precisely tries what you suggested, I think there are other issues. So it's like a balloon, you push it here and the air comes out somewhere else.
Thank you very much.
You're welcome.
Thank you, Yuri. We have another question in the chat by Guido Grützner, who asks how much of this general approximation is due to the push forward by ReLU networks? Wouldn't it also work with locally constant functions like trees?
Yeah, the answer is simple, yes. So if you like, why ReLU networks? So we were interested in trying or in understanding why GANs work so well. And that's why we started with neural networks. But you can abstract away, indeed. And you know, I talked about approximation theory before. With a ReLU network, you can approximate any function to within arbitrary accuracy. And so now you can forget about the neural network and say, well, I just do something, trees or whatever you have it, and I build this whatever you have it with a ReLU network. But as I said, our goal was to try to see why these GANs work so well in practice. And now, of course, you can say, well, these are trained GANs, they work so well, but at least you know that there exists a training algorithm that can in principle produce anything you wish. But once you're done with that, you can discard your ReLU networks and work with whatever your preferred choice of building blocks is.
Yeah, super, thank you. Are there more questions? Don't be shy. I was actually going to ask you about other types of nonlinearities in a network, which is a similar question, I guess. Okay, another question popping up. So I'm going to read your questions, but if you want to speak up yourself, just do it.
Okay.
Okay, Matteo, go ahead.
Thank you. So thanks again for the very, very interesting talk. Just out of interest, what is the reference that you cited for like the approach to train the last layer?
Yeah, I'm just trying to find it. Just if you give me a second.
Yeah, sure.
Yeah, I think I have it. So can I paste it into the chat?
Sure.
It's by Daria Fokina, and Ivan actually misspelled the name. It's Oselidets. So I'll just paste it into the chat.
Thank you very much.
You're welcome.
Great. So Helmut will be back also this afternoon if there are more questions coming to your mind. I think really, Helmut, I think I'm speaking for everyone. You gave a really, really wonderful talk that was very comprehensive and was really, really well explained. Okay, Helmut, thank you very much. Thanks so much. Let's thank Helmut again.
Thanks everyone for listening in. I appreciate it, and have a nice day.
Thank you. And I'll see you later. Yeah.
Yeah,
It's
okay.
going to be 5 p.m. for you.
For me, 5 p.m. Yes, I'm not going to miss it. Yes. Thank you, Carola, and thanks to everyone. And see you.
Thank you, Helmut. Thank you so